Good afternoon, everyone, and thank you for taking the time to join us today on this live webinar. As we get started, a few quick reminders. This is being recorded and the slides and video will be shared. All audio is currently muted, but we have set aside ample time for Q&A towards the end of the presentation. And this is the first of series of webinars dedicated to radio frequency intelligence from commercial providers. For today, we'll be spending the majority of our time discussing GNSS jamming detection and geolocation. I would like to start out by introducing your hosts today. My name is Ian Goodridge, and I'm currently responsible for managing the go-to-market for our radio frequency intelligence products. I'm joined by my colleague, Evan Starsinik, a former Navy surface warfare officer who now manages advanced programs for the US federal team here at Spire. Our guest speaker, bringing vast RF and geolocation experience, is Zach Clemens from the Department of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin Radio Navigation Laboratory. Jumping into our agenda, we're going to start out with brief overviews of both Spire and the lab at UT. From there, Zach will explain why we have a 50-watt light bulb mention here. And we're going to run through some fantastic recent RF intel results using Spire data. Evan, I'm going to unmute you and we can get into the Spire introduction. Thanks so much.
Thank you, Ian. So Spire is a cube satellite-powered space-to-cloud data and analytics company. We specialize in providing data-driven insights and predictive analytics to customers in a range of industries. The company was founded 11 years ago with the idea being to be completely vertically integrated other than launch. So building out a ground station infrastructure, designing and manufacturing our own satellites, and ultimately launching a proliferated constellation into low Earth orbit. Our models range from 3 to 16U, so think roughly the size of a loaf of bread, up to a small mini fridge. And up to this point in the company's history, we've launched about 160 total satellites, with over 100 currently operating in orbit. Now, the reason for the large number of satellites is ensuring that we have global coverage for timely and precise collection of the different types of RF data we're interested in collecting. We collect maritime, aviation, Earth intelligence, and weather data, maritime in the form of AIS, aviation in the form of ADS-B, and then GNSS reflectometry and radio occultation for our Earth intelligence and weather data products, respectively. Spire also offers what we call space as a service, because we found that we were very good at doing what we do, which is designing, building, and launching satellites. We expanded into the 612 and 16U models in order to offer our customers more flexibility in the payload space available. Our 34 ground stations globally and 70 antennas are what helps us with a timely data downlink, which really makes us effective at running the mission end-to-end for the customer while they focus on what they need to focus on the research and results side. Here's a slide dictating our product verticals. As I mentioned, maritime aviation, weather, and Earth intelligence in multiple use cases. Weather, we provide raw data as well as building out our own forecasts and offering a localized point forecast for customers. And then on the Earth intelligence side, we range from economic and agricultural use cases like soil moisture and wave height, surface winds, and tracking of ice in the polar regions, all the way over to radio frequency intelligence, which Ian is going to be talking about today. And with that, I would like to pass it over to Ian to talk about that more.
Thanks, Evan. That was a great overview. RF intelligence is a maturing field that has grown expeditiously since World War II and can roughly be defined as utilizing radio frequencies to infer knowledge. It is a technological field that is utilized by governments, companies, and agencies across the world for public safety, commercial insights, and defense purposes. Spire has developed deep expertise in monitoring radio frequency activity with a dedicated fleet of diversified, tunable RF payloads in space. For example, as shown in this table, Spire's GNSS RO payload satellites have 50 to 20 flybys on any given point of Earth that are viable for an IF collection for the purposes of geolocation. This has the potential to provide semi-continuous surveillance due to the nature of Spire's satellite orbits. That capability is active and taskable today. For a use case example more on the maritime side, we are also validating reported locations of VHF AIS transmissions in near real time, identifying an average of 35 unique MMSIs assigned to ships a day that are 100% falsifying their actual locations. We've even worked with EO partners to image and validate these events. I'll now hand over to Zach to cover his background at the University of Texas. Zach, thanks.
All right, thanks, Ian. So my name is Zach Clements. I'm currently a PhD student at UT Austin in aerospace engineering under Dr. Todd Humphreys in the radio navigation lab. We have a rich history of developing theory and technologies for secure and robust positioning. On screen, I've shown some of our current research interests, including GNSS interference monitoring, GNSS spoofing and spoofing detection, our recent work in LEO PNT, exploiting Starlink satellites for positioning, and then also software-defined radio, where we develop our own in-house boards and software-defined radios to pair with it, and also a commercial company, LocusLock, aiming to provide this to the mass market. So here are just a few of our research interests. More is available on our website. Thanks, Ian.
Thanks, Zach. That was great. So I'm going to keep you on the mic there, and we're going to jump into the next slide here. 50-watt light bulb. Why a 50-watt light bulb?
Perfect. Yeah, 50-watt light bulb. The point that we want to get across is that GNSS is fragile. Its service is easily denied by jammers or deceived by spoofers. And GNSS signals are especially vulnerable to jamming just because they are extremely weak near the surface of the Earth. They have no more flux density than a light received from a 50-watt light bulb at a distance of 2,000 kilometers away. So they are extremely weak and easily jammed. The civilian, maritime, and airline industries frequently encounter GNSS jamming and spoofing. Corrupted automatic identification system, AIS, and ADS-B messages from surface vessels and aircraft are often reported. Irregularities in these messages are often indicative of GNSS interference. And we've seen this across the globe, affecting both civilian and the military industries.
Great, fantastic, Zach. Thanks for that overview. I'm going to go ahead and pause the screen and send you the slides now, because I know you wanted the ability to kind of point out certain details of your slides as we go through there. So Perfect. Everyone, we're just going to stop sharing for a second, and then we'll be back with Zach's presentation. Okay, Zach, I just sent you the presentation.
Perfect.
We can see your slides. Thanks.
We can see everything just good. Let me see if I can flip. All right, perfect. So space-based GNSS interference monitoring has the potential to offer continuous global situational awareness and interference characterization. LEO is a perfect place because it's a nice sweet spot. You're close enough to the surface of the Earth to receive the terrestrial interference, but the standoff distance actually permits tracking the authentic GNSS signals, which is really important because it enables precise time tag data as well as precise orbit determination. Space-based jammer geolocation has been publicly achieved before. Previously, our lab geolocated a jammer operating out of Hamam Air Base in Syria using our lab's GNSS receiver on board the International Space Station. But localizing this jammer in Syria did hinge on a lucky break. The emitter was transmitting a signal from which a Doppler time history could be extracted. And with only a single satellite like we had here on the International Space Station, Doppler-based geolocation is the only way to precise geolocate emitters. But with multiple satellites, such as a constellation of satellites like Spires, you can geolocate any arbitrary waveform accurately. So today I'll be focusing on dual satellite geolocation. So here is the model that we are working with. We will assume the transmitter to be stationary on the surface of the Earth, and we'll have 2 LEO-based receivers. These spatially separated LEO receivers will receive the same signal at different times and at different frequencies just due to the geometry of the receivers. These physical characteristics of the received signal will form the basis for emitter geolocation, namely the time difference of arrival measurements, the TDOAs, and also the frequency difference of arrival measurements, the FDOAs. So let's talk about a recent capture. During April of 2022, 2 Spire satellites performed 2 consecutive 60-second dual frequency simultaneous captures over a very interesting area. So the first capture, here are the ground tracks of the satellites during the first capture, and then here are the ground tracks of the 2 satellites during the second simultaneous capture. The raw samples on both L1 and L2, along with the onboard navigation solution, were downlinked for post-processing. So here is just a quick look at what the power spectrum was looking like, and you can see that there's composite wideband interference on both L1 and L2. Remember, under no interference, the power spectrum would be perfectly flat, just because it would be noise. And you can see L1, what's interesting about L1, it contains multiple continuous wave chirp jammers, as well as other wideband interference. And here is just a zoomed in of these chirp jammers right here. The approximate parameters are listed above. And then also on L2, we see there's a very strong narrowband source as well as other wideband interference. Not only that, we also can see some long range air surveillance radars operating near L2. So there's obviously a lot of stuff going on in both GPS L1 and L2, and we want to be able to geolocate where everything's coming from. So let's now get into the geolocation aspect of it. So here is an overview of the traditional 2-step TFDOA geolocation approach, where it consists of 2 steps to get the emitter position estimate. First, a time series of time and frequency difference of arrival measurements must be generated. Then once you have a time series of measurements, those can be thrown into a nonlinear estimator to ultimately estimate the emitter's position. So you might be wondering how we estimate the time and frequency difference of arrival. Well, we do it by cross-correlating the received samples on each receiver via the complex ambiguity function, the CAF. So what will be referred to as the CAF domain. And it's been shown in the literature that the TDOA and FDOA that maximize the magnitude of the CAF, so here's an example CAF right here, the TDOA and FDOA that maximizes CAF, this point right here, that corresponds to the maximum likelihood estimate of the time and frequency difference of arrival between a pair of receivers. The second step, and you generate the CAF at each time instance you want a measurement. So you get a time series of measurements from the CAF, and now the second step is nonlinear estimation. So recall here are the equations, the measurement equations for the time difference of arrival and the frequency difference of arrival. Every time an R term appears, that contains information about the emitter's position. So we can tailor a nonlinear estimator specifically for these measurements to estimate the emitter's position. In our case, we just used nonlinear least squares and a Gauss-Newton. And we also used an altitude constraint to increase the observability of the problem. But you can find the full estimator in a paper I recently wrote about this. So let's get back to the real data. What's shown here is a CAF during on L2 during the first capture, and you can see there are multiple peaks everywhere, meaning that there are many peaks or many transmitters in the received data. So you can see there's a clump of peaks right here. Each one, there's only a single one. That's nice. But then what's also interesting is that you see these 3 peaks repeating every 1 millisecond. That's because these signals are cyclostationary. And what cyclostationary means is that they have statistical properties that recur cyclically over time, which makes for repeating patterns in the CAF, which could potentially cause an ambiguity. But in our case, for this individual emitter, let's focus on this peak right here, the loudest one. And you can see that it's not cyclostationary just because there aren't any repeating patterns. So this peak right here corresponds to the TDOA and FDOA of the signal at that time instant. So we generate the CAF over time and track this peak. And we ultimately get a time history that looks like this. So here's a time history of the TDOA measurements, and then the time history of the FDOA measurements. And now that we have a time history of these measurements, we can use our nonlinear estimator that we tailored specifically for this purpose. And sure enough, it lands on top of the Hemem Air Base once again in Syria. So if you recall earlier, this is where we found a jammer back in 2018 using data from the International Space Station. Here is the formal 95% air ellipse with semi-major and semi-minor right here, and then also the post-fit measurement residuals, and they're all nice and zero mean, meaning that we've modeled appropriately and our estimator is locking right onto the true solution. So yeah, this was a great geofix to get us started. So that was all on, or that CAF I was showing before was on L2. Let's go back to L1, and if you can recall, there were the very powerful chirp jammers. You can see the CAF on L1 is kind of nasty. There's a lot of structure going on. We can isolate the higher bandwidth chirp jammer from the lower bandwidth chirp jammer just by passing it through a high pass filter. But even then, we get rid of all of the spectral content from the lower chirp jammers, but you can see that there are still many peaks going on. There's one true max, but all these other peaks are hard to deal with. So if you were to actually deploy this, your multi-target peak tracking algorithm would just struggle just because of all of these side loops. But I ended up tracking the peak over time and getting a time history of the TFDOA measurements, and then I used our nonlinear estimator, and sure enough, it landed in northern Israel. And you can see right here, there's some very interesting equipment nearby. So this was a manual track by me tracking this peak. We want a better way just to deal with all of the irregularities, all the repeating structures due to the waveform. So problem with two-step TFDOA geolocation, it's difficult to track and associate peaks in crowded signal environments. Undesirable structures in the CAF due to the time correlation properties of cyclostationary signals can cause issues, as shown with the chirp jammer and also the other run of peaks I showed earlier. And then also the weaker signals end up becoming harder to detect and track just because your coherent integration length is limited. So let's move on to direct geolocation. Direct geolocation, you see now, to get a position estimate, all you need is a single step. So this is also known as a single step approach. And how this works is that you define an area of interest, so you deploy a grid, and then at each point in the grid, you assume the transmitter to be there. So at this point right here, we assume the transmitter to be right here, and we know where our receivers were, so we can calculate the expected time and frequency difference of arrival corresponding to this geometry. And not only that, we can convert the frequency difference of arrival to a set of phase offsets, meaning that we can ultimately coherently integrate longer, just because we can now deal with changing FDOAs just because we can directly parameterize for the phase offset. So at each point in the grid, we calculate the position domain correlation value. And what will end up happening is the maximum value, the maximum point in the position domain will correspond to the maximum likelihood estimate of the emitter's position. And this was shown by Weiss back in 2014. So what's nice about the position domain correlation is that no intermediate measurements are involved. There isn't any loss there which would happen in the two-step approach. Not only that, we can also directly implement a terrain model for the altitude. So for at each latitude and longitude pair, we can fetch the altitude from a terrain map. So here now is direct geolocation over the airbase. We defined our grid, and then each point on the z-axis here is our position domain correlation value. And you can see, and here are 3 different coherent integration lengths, and you can see how over time, or as you increase your coherent integration length, the ridge becomes sharper and more pronounced. In the peak of all 3, they also correspond, the peak corresponds to the same position estimate that we got with our two-step approach, which is really reassuring, because now we know with, in this case, a high SNR signal, our two-step and our single-step solutions correspond. But one trick with the direct approach is that the longer you coherently integrate, yes, the peak will become sharper and more pronounced, but you really need a finer grid, otherwise you risk the peak falling through the cracks. So let's go back to the L1 chirp jammer and how I was complaining about this could be hard to track. Well, now that we know it's coming from northern Israel, we can deploy our grid on top of Israel, and we can calculate the position domain correlation. So you can see here, here's our grid, here is the correlation values, and you can see we see a nice sharp peak here. You might also be thinking, well, this still kind of looks nasty because of all the other spurious side lobes, but we can deal with that. We can deal with that by computing the position domain correlation grid over time. So you can see I'm keeping the grid the same, and I'm doing the position domain correlation over time. And you can see how over time it changes. And that's just because of the geometry of the receivers at each instant. I'm creating this position domain correlation grid. And then when we non-coherently combine all of these grids, so we non-coherently integrate all of these grids, all of the side lobes seen over here end up averaging out and reducing down to the noise floor. And the only thing that remains here is this sharp peak right here, corresponding to the emitter position estimate. And then once we, here's our non-coherently combined grid. Here's a contour of this non-coherently combined position domain grid. And sure enough, we get the same solution that we got with the two-step approach. But what's advantageous about this is that we didn't have to deal with any sort of peak tracking. All the side lobes end up reducing down to noise in the position domain. So this is just much more preferable. So advantages of the direct geolocation approach: there's no need to worry about tracking and associating peaks in the cap because the emitter position just becomes directly from the raw samples. It's better for short captures and low SNR signals just because the samples can be coherently integrated over longer intervals because we're now directly parameterizing for phase. And also, as shown with the chirp jammer, it's better suited for waveforms that produce undesirable structures in the calf, namely these cyclostationary signals. So let's get into more real-world jammer geolocation from this same data set. In 2018, at the time, the General Raymond Thomas said, right now in Syria, we're operating in the most aggressive electronic warfare environment on the planet. Well, what do we do with that information? Let's deploy a grid pretty much over the entirety of Syria, and let's see what we find. And this is what we end up getting. So with the same grid, I computed the position domain correlation once a second over every 58 seconds. And our grid spacing was 0.01 degrees in latitude and longitude. So we had 58 position domain grids. We non-coherently integrated all of them, and this is what we get here, which was just amazing. I mean, we see peaks everywhere. Each peak in the position domain represents a jammer position estimate. And just here's a view to let you appreciate how powerful this is. So on the x-axis is longitude and this is latitude, but at each peak on this grid represents a jammer position estimate. And we can see that there are many jammers on L2. So this was on L2 during the first capture. I repeated this same process on L1 of the first capture, and then on L1 and L2 of the second capture. And I took the peaks from the position domain, and we put them on this map here. And you can see there are jammers everywhere. So this right here is the Khmeimim Air Base, as shown before. We can see that we were able to get a peak there on both L1 and L2 on both captures. These peaks over here, you can see they're in blue. We managed to get a peak there on the first capture on L1, and then on the second capture on L1, but it wasn't transmitting on L2. And then over here, the red peaks, we were able to get a solution on the first capture on L2 and also the second capture on L2. So a lot of these peaks, we're seeing tight agreement across multiple passes, so first capture and second capture, but not only that, we're getting agreement on multiple frequencies in these cases over here. So this leads us to believe that these are real jammer position estimates. Let me take you on a tour on some of these. So let's first zoom in here. Now that we know loosely that it's the jammers in the area, we can deploy a finer grid as such outside of Mosul. And sure enough, so this is a contour of this direct geolocation grid right here. And if you zoom into right here, we see equipment, which leads us to believe this is a plausible emitter position estimate. So once again, here's the position domain grid. The peak corresponds to the jammer position estimate. And then imagery from Google Earth, leads us to believe this to be a plausible location. Not only that, let's go over here now to Tartus. It is known that the Russians operate a naval port out of there. Here is our fine direct geolocation grid. Here is our contours of this grid. And sure enough, we see things that would be indicative of where a jammer would be. This is an image taken from Black Sky a day after the collect. And you can see right here, these three ships right here are military ships. So that could be a plausible source. Let's go to right here. This actually ends up being Sarmin, Syria. And I'm just showing right now, I got a two-step solution on here as well as a direct. I'm just showing the two-step solution right now because we have a 95 semi-major and semi-minor. But if you zoom in right here, once again, we see equipment and fortifications that strengthen our argument that a jammer is indeed there. And if you repeat this across all of our other geolocation estimates, you'll see similar fortifications and equipment. And these images right here were just taken from Google Earth, all publicly available. In the second capture, we are also able to see, get a glimpse of Ukraine. And here are two jammer estimates that we got right here. This was where the Russian front line was during April 2022, then also north of Kharkiv. These are both, contested areas. So takeaways, deliberate, unauthorized, wide area GNSS interference is ongoing in multiple areas of the globe. Time-synchronized LEO-based receivers provide unprecedented levels of GNSS interference detection and geolocation. Not only that, emitters transmitting arbitrary waveforms can be geolocated with sub-kilometer accuracy, and direct geolocation outperforms the traditional two-step approach in these regimes with short time captures, low SNRs, crowded signal environments, and also structured cyclostationary waveforms. So with that, I will throw it back over to Ian.
Zach, thank you so much. That was a fantastic overview. I know we've got quite a few questions coming in already regarding some of your work there, so thank you for that. I do encourage everybody. There is a Q&A tab in the GoToWebinar box. Please pop your questions in there. We'll do our best to get to those. If not, we will follow up later as well. Before we get into the Q&A though, Zach, would you mind going forward a slide for me?
Yep.
I did want to just highlight that we're not talking about a theoretical here. I think obviously Zach's work is under his lab and under his kind of purview, but from the Spire side, we are delivering this data every day. We're building a large archive of this information over various hotspots around the world. And we're actually very, very capable of adjusting those areas, pretty rapidly for new areas of interest, new signals of interest. As we touched on, obviously a plus for us is the number of GNSS receivers we have in space that can perform this work. So I did want to, really encourage the audience, if there's legitimate projects or customers that you're working with that are interested in this raw IQRF data and potentially geolocation reports as well, please reach out to the team here. You can start with me or you can start with Evan. And with that, I think we'll jump into the Q&A. So if you one more slide forward, Zach, and then you'll be good. So we've got a few that came in a little bit earlier. Zach, this one may be for you. So if you don't mind, coming from a gentleman in the audience, Ryan, can you talk about your trade-offs which might exist by using CubeSats for RF surveillance versus larger satellites with more power and instrumentation? So really kind of talking about the LEO concept versus others.
Yeah, LEO's nice just because of, quite frankly, how fast they're moving, right? I mean, in low Earth orbit, they'll traverse the globe in 90 minutes, so you can get a nice constant refresh rate. Also, being really fast helps us in TFDOA and direct geolocation, just because let's just say over 60 seconds, the satellites cover much more geometry over that 60 seconds than if they were further out in space. So the measurement diversity that we get from that is huge, making the geolocation estimates much more accurate. Bigger antenna, or if for the bigger satellites, they might have better antennas on board, or they might even have more other equipment. Maybe they can do they have a phased array, can do angle of arrival. That might be helpful. But we've shown with this that all you really need is just an antenna pointing downwards toward the surface of the Earth, and then also on board, what you need is a zenith-facing antenna to maintain accurate positioning and timing on board the satellite. So yeah, LEO satellites are nice because they're cheap, and we were able to achieve a lot with not the most advanced set of hardware.
Hey, thank you, Zach. Another good question, gentleman Richard, asking a question. This actually will be another one of this webinar series that we're planning as well, but getting into more of the signal spoofing. So the question is, can you also use these techniques for signal spoofing, and are they harder to find? So Zach, another one for you.
Yeah, actually, for sure, you definitely can. Actually, I published a paper back in September 2022 unveiling a technique applying specifically for GNSS spoofers with only a single satellite. Spoofers are a little bit trickier just because they don't transmit at a constant carrier. It's changing because the spoofer has to vary its frequency given the geometry of the satellite it's trying to spoof and the intended spoofed position, which makes things a little bit trickier. But I did write a paper on that, back in September, which would be worth a read, I think. But also, I mean, that's only with a single satellite, and with 2 satellites, you shouldn't have any issues at all dealing with it. If you have 2 satellites, there's really nowhere to hide.
Great. Thank you, Zach. There's a question here from Paul referring, and I think this is quite interesting. I think you may know more about our constellation here, but there's a comment that Spire appears to have a lot more kind of single opportunities to collect, single satellite collection opportunities, just for the nature of the constellation. What is your opinion on what kind of geolocation accuracy should we be able to expect from a single satellite collection?
Yeah. It's dependent on what waveform the transmitter is transmitting. So if it were transmitting something like say if it was a match code jammer where it's transmitting a GPS-like signal, you can really get nice, clean Doppler measurements from that, and you can probably get sub 10 kilometer estimates from that, only with not too much. You don't need multiple passes. You can only you can get that on a single pass. Not only that, if you're only using a single satellite, that's nice just because of how quickly you can downlink it. But yeah, single satellite's exciting just because I feel like it can give you good estimates, and not only that, the complexity in terms of scheduling captures and performing the captures is much lower. So they're nice and easy.
Great, thanks. And then maybe just a clarifying question, Evan, you're welcome to take this one. There's a question here that talks about, on your intro, you talked about space services for kind of custom payloads and things like that. Would it be possible to build or to contract a kind of our own RF intelligence gathering satellite constellation? Evan, you want to take that?
Yeah, certainly. That is definitely within the realm of capabilities for our space services team. We can do single for testing up to clusters and even full constellations as well.
Excellent. And then I was going to say we'll probably wrap up there, give everybody the 20 minutes. I know we allocated an hour, but we have 2 questions coming in, actually 4 questions coming in just then. I shouldn't have said that, should I? So first question, Zach, how do you deal with saturation from strong signals? What's your point of view on that one?
Oh, yeah. That's just dependent on whatever hardware you have on board the satellite. So, if there's if they're too powerful, right, the automatic gain control will just saturate, and there's nothing really you can do about that. We do have an automatic gain control on board that seemed, or we didn't have any issues with it on the capture that I looked at. But yeah, that could definitely be an issue. But what's nice about LEO is that we're far enough away that unless they're beamforming right at our satellite, I don't expect there to be too many issues.
Okay, thanks. There's a question, do we offer raw IQ? The answer to that is yes, absolutely. And we can deliver that via many different methods. Our preferred method there is literally just dropping it into a secure bucket, GovCloud or AWS. And then there's a question, and then I think this will probably be the last one we'll take, and apologies if we don't get to everybody, we'll follow up offline. The question is about, do we cover other signals? And that, no problem at all. Actually, absolutely, yes, we do. We're active in VHF and broader L-band, so SATCOM. And then roadmap-wise, we have a pretty strong roadmap to pick up some of the maritime radar and other radar bands as well, just to answer that question directly. And then one more question about other materials. Absolutely, we have detailed white papers, case studies, full presentations, and lots of other kind of customer testimonies as well we can share. So thank you for asking for that. With that, I am going to thank my co-presenters. Zach from the University of Texas, thank you so much. Evan, thank you for your overview and questions. And we will wrap this presentation. And as I mentioned earlier, thank you everyone for the attendance. We will get the Q&A, the presentation, and the slides sent out. And we look forward to inviting the rest of you back to the second one, which will be dealing with signal spoofing, as it was mentioned in the Q&A. So thanks everybody, and have a great afternoon.